Hi, dual nature of matter comes out clearly from what we have learned in this and the preceding chapters. The wave nature of light shows up in the phenomenon of interference, diffraction, and polarization. On the other hand, in photoelectric effect and Compton effect, which involve energy and momentum transfer, radiation behaves as if it is made up of a bunch of particles called the photons. Whether a particle or wave description is best suited for understanding an experiment depends on the nature of the experiment. For example, in the familiar phenomenon of seeing an object by our eye, both the descriptions are important. The gathering and focusing mechanism of light by the eye lens is well described in the wave picture, but its absorption by the rods and cones requires the photon picture of light. A natural question arises: if radiation has dual nature, the particle of nature also exhibit wave-like character. The French physicist Louis Victor de Broglie that put forward the bold hypothesis that moving particles of matter should display wave-like properties under suitable circumstances. He reasoned that nature was symmetrical and that the two basic physical entities, matter and energy, must have symmetrical character. If radiation shows dual aspects, so should matter. De Broglie proposed that the wavelength lambda associated with a particle of momentum p is given as lambda is equal to h by p, which in turn equal to h by mv, where m is the mass of the particle and v is its speed. This equation shows, or known as, de Broglie relation, and the wavelength lambda of matter wave is called de Broglie wavelength. The dual aspect of matter is evident in the de Broglie relation. On the left hand side of this equation, lambda is the attribute of a wave, while on the right hand side the momentum p is a typical attribute of a particle. Planck's constant h relates the two attributes. Equations for a material particle is basically a hypothesis whose validity can be tested only by experiment. However, it is interesting to see that it is satisfied also by a photon. For a photon, Einstein gave the relation P is equal to h nu by c. Therefore, h by p is equal to c by nu, which is equal to lambda. That is, the de Broglie wavelength of a photon given by the equation equals the wavelength of electromagnetic radiation of which the photon is a quantum of energy and momentum. Clearly, lambda is smaller for a heavier particle, for example large m, or more energetic particle large v. For example, de Broglie wavelength of a ball of mass 120 gram moving with the speed of 20 meter per second is easily calculated as lambda is equal to h by p, that is equal to 2.76 into 10 to the power minus 34 meter. So we can easily verify that for a greater mass particle, a particle with a greater mass, its value of lambda wavelength is too much small. We cannot detect that as a wave. So we attribute there is a little suitable shows appearance of a wave.